Activation energy. The minimum amount of energy which a reactant must require to go into product is called activation energy. EA is equal to energy of activated complex minus energy of reactant molecules. Energy is released when activated complex decompose to form products. Profile of energy when reactant go into products is represented by the following A activated complex diagram. Potential energy. Reactions coordinate exothermic reactions. Reactions coordinate endothermic reactions. Potential energy. Activated complex. All the molecules in the reacting species do not have the same kinetic energy. The fractions of molecules with a given kinetic energy is calculated with using Boltzmann and Maxwell statistics. Ne upon Nt is equal to e to power minus e upon Rt. The factor e minus e upon Rt is called the Boltzmann factor. It represents the fractions of molecules Ne upon Nt having energy equal to or greater than E, where Ne represents number of molecules with energy. E and Nt represent the total number of molecules. Distributions of kinetic energy may be described by plotting a graph between fractions of molecules and the kinetic energy. The peak of the curve corresponding to the most probable kinetic energy. Fractions of molecules, most probable kinetic energy. Kinetic energy distributions curves showing energies among gaseous molecules. Fractions of molecules, kinetic energy, energy of activations T plus n. This area shows a fractional of molecules which react at T. This area shows fractions of additional molecules which react at T plus 10. Distributions curves showing temperature dependence of rate of our reactions. When the temperature is raised, the maximum of curve moves to higher energy value and curve broadens out. Thus, the proportions of molecules with higher energy increases, that is, the fractions of reactant molecules which collide with energy greater than EA increases with increasing temperature. According to arrhenius equations, K is equal to AE power minus EA upon RT in K is equal to minus EA upon RT plus in A, or log K is equal to minus EA upon 2.303 RT plus log A. Plot. The plot of log K versus 1 upon T gives a straight line with slope is equal to minus EA upon 2.303 R and intercept is equal to log A. Log K2 upon K1 is equal to EA upon 2.303 R in bracket 1 upon T1 minus 1 upon T2, where K1 and K2 are the values of the rate constant temperature T1 and T2 respectively. Log 10K 1 upon T, a plot between the log K and 1 upon T. Log A slope is equal to minus EA upon 2.303 R. Effect of catalyst on the rate of reactions. A catalyst is a substance which increases the rate of reactions without itself undergoing any permanent chemical change. Catalyst provides an alternate pathway or reactions mechanism by reducing the activation energy between reactants and products and hence lowering the potential energy barrier as shown in figure. A catalyst does not alter Gibbs energy. Del G of a reactions, it catalyze the spontaneous reactions but does not catalyze non-spontaneous reactions. A catalyst does not change the equilibrium constant of a reactions, rather it helps in attaining the equilibrium faster. An example of a reaction showing a small negative temperature coefficient, that is in which the rate of reactions decreases with increase in the temperature, is NO plus 1 upon 2 O2 NO2. Collision theory of chemical reactions. According to this theory, the reactant molecules are assumed to be hard sphere and the reactions occurs due to the collision of molecules. All the collisions are not effective. Effective collisions are those collisions in which molecules collide with sufficient kinetic energy called threshold energy, which is equal to activation energy plus energy possessed by reacting species and proper orientations. Rate is equal to P ZAB power E minus EA upon RT, where P is equal to probability or steric factor, which takes into account the fact that in a collision molecules must be properly oriented, and GAB is equal to collision frequency, that is the number of collision per second per unit volume of the reactions mixture of reactants A and B. Thus, in collision theory, activation energy and proper orientations of molecules together determines the criteria for an effective collision and hence the rate of chemical reactions.